Welcome to the video lecture on applications of logs and exponentials. In this video, we're going to talk about various real-world applications that can be modeled using logarithms and exponential functions. Many natural phenomena follow the principle that the rate of growth or decay is proportional to the amount present. A model which will represent this situation is A equals A sub 0 e to the kt, where t represents time, a sub 0 is our original amount, or whatever the amount is at time equals to 0. A is the general amount present at any time t, and k is a non-zero constant representing the relative rate of growth or decay. One common example that you already know about is the growth of money in an interest-bearing account. And it's an example of such a phenomenon. We all know this as the PERT formula, A equals PE to the RT, where the A sub 0 is what we call the principal P. So let's practice using this for a moment. Suppose that we want to find the time it takes for an investment to double if the interest rate is 8% compounded continuously. Now you need to see that phrase continuously, or compounded continuously, in order to know that you should be using this PERT formula. And if we are using it, then we want to figure out what all of these various letters represent in this problem. So what we want to know is the time it takes for the investment to double if the interest rate is 8%. So they don't really tell us a whole lot of numbers here. The only number that I see is this 8%, which is going to be my interest rate. And remember that you want to use that as a decimal, so 0.08. We're looking for a time, so that means the variable that we're trying to solve for here is t, so I'm going to leave my t in here. And that means I need to know what p and a are, but they don't really tell me what my initial principal is, and they don't give me a specific number for what this a is supposed to be. However, they give me a relationship. They tell me that we want our investment to double. So even if I don't know what my initial principal is, I'm going to still call it P. I know that the time that I'm looking at is the time it takes for this principal to double. So in this account, we want to end up with 2 times P to double. So that's a way that we can get around the fact that we're not told what this initial principal is. But even though this looks like a 2-variable equation, it turns out not to matter what that p is, because in the very next step of solving, we would want to get rid of that coefficient in front of our exponential expression, because you want to isolate this exponential as much as possible. So any coefficients in front need to be divided, any numbers off to the side would have to be added or subtracted over first. And when I divide through by this p on both sides, it cancels on both sides. So we're left with just a 2 equals e to the 0.08t. And now this becomes a 1-variable equation, so we should be able to solve it. Now the variable t is up here in the power, and the only way to get to that t is to undo this exponential. So what's going to undo an exponential that has a base of e? Well, it's going to be a logarithm with a base of e, otherwise known as an ln. So we're going to take the ln of the left side and set it equal to the ln of the right side. Ln is base e, so ln base e cancels with this exponential base e, and these will cancel each other out, just giving me that power 0.08t. And then to finish solving for t, I'm just going to divide both sides by 0.08. And the exact value would be ln of 2 divided by 0.08, but this is a word problem, so usually in these cases we do want to get a decimal approximation. So let's go ahead and figure out ln of 2 divided by 0.08, and we get 8.66, I'll round up to 2 decimal places. And what are the units that we're talking about here? This is time. And so we're going to, since this 8% was compound, the interest rate for the year, we're going to assume that our units for our time are also years. So it's going to take close to 9 years, a little more than 8.5 years, for our money to double. Okay? Now that was the PERT formula, which models how to calculate the amount of growth of money in an interest-bearing account that's being compounded continuously. We're going to see another example, very, very similar in the formula, but for a totally different situation. So this time we're going to talk about population size. And we have a model which describes the size of a population at time t, given by this formula, P of t, for the population at any time t, is equal to P sub 0 e to the RT, where again R is the relative rate of growth of this population, and P sub 0 is the initial population. So it's very similar, almost identical to that PERT formula, but this time we're thinking in terms of population sizes instead of the amount of money in an account. So let's talk about a bacteria population with an initial size of 400 that we know triples in half an hour. Find the model that represents the population. So when it asks us to find the model, that means it wants us to come up with what this formula right here is going to be in the context of this problem. So we need to figure out what our P sub 0 is, and we need to figure out what our growth rate R is going to be, and then we'll have a formula that will enable us to predict the population at any time t. So what do we know so far? We know that the initial size of the population is 400. So right away that tells us that our P sub 0, our initial population, is 400. It doesn't tell me in this problem what the R is, what the rate of growth is as a percent. I don't see any percents given to me in this problem, but it does tell me that the population triples in half an hour. So when time is 1/2, half an hour, then the population is going to be triple. So triple what? Triple the initial size. So 3 times 400 means that the population is going to be up to 1,200 in just half an hour. So we're going to use that information, that T and that P, to substitute into this model so that we can try and figure out what the what the growth rate R needs to be. So here's our general formula. P of t equals P sub 0 e to the RT. I know what my P sub 0 is, it's 400. I don't know what my R is, that's what we're trying to solve for, but I do know a T right here and a P right here that go together. So we're going to substitute in 1/2 for the time and 1,200 for the population. And now this creates a one variable equation that we can hopefully solve for R. Alright, so what do we do first? Well, if we want to get at this R, we need to isolate our exponential. So that means always divide through by this coefficient first. So we're going to divide both sides by 400. 1,200 divided by 400 is 3. So we get 3 equals e to the 1/2 R. And now we are ready to undo this exponential base e because it's isolated, and we're going to use an ln to do that. So ln of 3 equals ln of e to the 1/2 R. The ln and the e cancel out, just giving me 1/2 R. And finally, to finish solving for R, I can undo this multiplication by 1/2, or you could also think of it as division by 2, by just multiplying both sides by 2. So my R is going to be 2 ln of 3. Now, what do we put for our final answer? Well, we're trying to put our model. So our final answer should be this generic formula right here for what P of t is going to be at any time t. So our model, or our formula, is the population P at any time t is equal to P sub 0, which we know was that 400, e to the RT. And now that I know what R is, I'm going to substitute it in. So we get 400 e to the 2 ln 3 times t. Now you could get a decimal for what R is, but I prefer to leave it as 2 ln 3. That way it's more exact, and as we continue with this problem further down here, we're not going to lose any accuracy by having rounded off to a decimal. So try to leave your R in its exact form throughout the entire problem until the very last step when you're trying to substitute it into your calculator. So now that we have this model, we should be able to predict the time it takes for a population to get to a certain size, or the population size that we get at a certain time t. So either I'm going to give you t and ask for p, or I'm going to give you p and ask for t. So let's see what this next question is asking us to do. It says determine when the population reaches 1 million. So this 1 million, that's a population size, that's a p, so I want to put 1 million right here where that p is. So we're trying to figure out when will this function, when will this model equal to 1 million. So I'm going to set it equal to 1 million, and I'm going to solve this for time, for t. So first thing I'm going to do, as always, isolate that exponential. So I'm going to divide both sides by 400. And when I do that, a couple zeros are going to cancel out, and we get 10,000 divided by 4, which is 2,500. And now my exponential is isolated, so I'm ready to take the ln of both sides. And the ln and the e cancel each other out, so we just get 2 ln 3 times t equals ln of 2,500. This 2 ln 3 is being multiplied by t, so to undo that, I'm just going to divide both sides by 2 ln 3. So my time is ln of 2,500 divided by 2 ln 3, and we're going to want to get a decimal for that. So let's type in ln of 2,500 divided by, make sure you use parentheses around your denominator, 2 ln of 3, close the parentheses on the 3, close the parentheses on the denominator. So our final decimal here, I'm going to round it off to 2 decimal places, would be 3.56, and it should be in the same units that we were using up here, and since I used 1/2 hour, that means this is also going to be in hours as well. So it's going to take me 3.56 hours for this population to reach 1 million. So pretty quickly these bacteria will grow. Now what we're going to do is find out how many bacteria are present after 75 minutes. So this time we're given a time, a t, that we're going to substitute in up here, and we're trying to find out a population size. Now the only catch here, and we just talked about this a second ago, is units. When I was finding this relative growth rate, R, I was using units of hours. So you want to be consistent with that. So this t in this formula represents hours. But in this problem down here, we're looking for 75 minutes. So you will need to convert a little bit here to make sure that you're using hours in our model. So 75 minutes, if I want to convert that to hours, there are 60 minutes in 1 hour, so we're just really doing 75 divided by 60, which is the same as 1.25, 1¼ hours. So instead of substituting in a t of 75, we're going to be substituting a t of 1.25. And I'm plugging it in right up here. So we're going to be finding p equals 400 e to the 2 ln of 3 times 1.25. Now this is the easy case, because when you know t and you're looking for the population p, that is just a calculator question. We don't need to solve anything here. We just need to type all of this into our calculator. We just need to make sure we do it very carefully. So this is going to give us 400 e raised to the 2 ln 3 times 1.25, and I get 6235. And I'm going to round off to just the whole number here, because what is it that we just found? We found a population size, and so it doesn't make sense to have a fraction of a bacteria. So this is going to be a population of 6,235 bacteria. And that is consistent and makes sense compared to our last solution. It took us 3.5 hours to reach 1 million, and after just 1¼ hours, I'm up to 6,235. So estimate-wise, this looks pretty good. Okay, another common type of word problem that you'll see with exponential growth and decay is radioactive decay. And this is exactly the same, or it's analogous to population growth, except that instead of growing in population size, the mass is going to decrease instead of increase. So we're going to set up a model to represent the amount of radioactive chemical present if we have 10 grams present initially and the half-life is 1,000 years. So we are going to use exactly the same model that we did before. So this P of t equals P sub 0 e to the RT. But this time we're not thinking in terms of time and population. This time we're thinking in terms of time and an amount of this radioactive chemical. So what do we know initially in this problem? We know that we're given 10 grams present initially. So that means our P sub 0 is 10 grams. So I can substitute in 10 for this P sub 0. Do I know my R, my growth rate, or actually in this case my decay rate? No, I don't. So we're going to have to first solve for R so that we can then write down what our generic model is going to be. So kind of like the last example that we did up here, where first we had to know a T and a P that went together so that we could substitute them in and solve for this R so we could come up with our model. We're going to do exactly that same thing. So we need a T and a P that go together so that we can plug them in. And that's where this half-life comes in. So the half-life means the amount of years it takes for your chemical element to decay to exactly half of its size. And it's when it refers to a half-life, it's talking about the years that it takes. So here, this is a T value. This half-life is a T value. So the half-life is 1,000 years. And that's the time it takes for this radioactive element to decay to exactly half its initial size. So if we started with 10 grams, then in 1,000 years, we're going to be left with 5 grams. So the P and the T that go together here are 5 is the P, so I'm going to substitute that in for the P on the left side. I don't know my R, but the T that goes with this 5 is this 1,000 years. So this is the equation that we want to solve to figure out what our rate of decay is. So in order to get at this R, we need to isolate our exponential. So I want to divide through by that 10 right away. Now 5 divided by 10 is a half. I'm going to use a decimal here. I'm going to use 0.5. And I get e to the 1,000 R. And then to solve for that, we want to undo the exponential. So I'm going to use an ln of both sides. ln of 0.5 equals ln of e to the 1,000 R. The ln and the e cancel out, just giving me that 1,000 R. So to solve for R, we're going to divide by 1,000. So my R is ln of 0.5 divided by 1,000. And just a little note here, this is actually a formula that works every time. So the rate of decay for half-life is always R equals ln of 0.5 divided by whatever your half-life is. So I'm going to call that H. So this is a formula that you can use to avoid having to reproduce this work every time, because the same thing is going to happen each time you're talking about half-life. This ratio that we got right here will always equal to a half. And what you end up with in the denominator down here is exactly the number of years that that half-life represented. So if you want to use this kind of shortcut formula to figure out your rate of decay, if it's a half-life problem, feel free. So what this means is now that we know what our R is, we can write out our model. Our model P of t is going to be this P sub 0, which was that initial 10 grams, e raised to this R. So ln of 0.5 divided by 1,000, there's my R, times t. And again, I'm going to try to leave it in that exact form so that I don't lose any of my accuracy. So there's my model. Let me copy it down here so that we can refer to it in the next problem. So just like in the last example that we did, now that we have this model, either I'm going to give you a t and ask for a p, or I'm going to give you a p and ask for a t. Those are the only kinds of questions that I could ask. So let's see what this next example is asking for. Determine the amount present after 140 years. So this 140 is obviously years, which makes it a time. So I'm giving you a time t, and I'm asking for the amount present, which is this p of t. So we're going to substitute in 140 for this t, and my units are good because my half-life was in years, and this 140 is also in years, so they're consistent units. And this is the easy case. When I give you t, you're just going to be able to plug all of this directly into your calculator. So let's go ahead and do that. We get 10 times e to the ln, whoops, too many ln's there, ln of 0.5 divided by 1,000 times 140. And I get 9.075. And what are the units on this? What did I just found? I found the amount of this radioactive chemical that's present. And remember, initially in the problem, the initial amount that I had was in grams, so this would also be in grams as well. So after 140 years, I've gone from 10 grams down to 9.075 grams. Radioactive decay is a very slow process, usually. Alright, let's try the next example. This time we want to find how long it takes to have 6.1 grams present. So remember what our model was. P of t equals 10 e to the ln of 0.5 over 1,000 times t. And this time we are told 6.1 grams. That's the amount present, so that's going to be our p, and we're trying to find out the time, how long it takes. So this time I'm giving you p and I'm asking for t. So we're going to put 6.1 on the left side, and we're going to leave t in there as t, and we're trying to solve for t. So the first thing that I'd want to do, if I want to get at this t, I need to isolate my exponential, so I'm going to divide through by 10. And that's just going to shift this decimal one spot to the left. So this becomes 0.61 equals e to the ln of 0.5 over 1,000 times t. We're ready to take our ln's of both sides. That ln is going to cancel out my e, so these cancel out, giving me ln of 0.5 over 1,000 times t. Whoops. And then here you just want to be a little bit careful because t is being multiplied by this fraction. So what I want to do is multiply by the reciprocal to undo that multiplication. So we're going to multiply both sides here by 1,000 over the ln of 0.5. And that should cancel these two guys out, and that's going to give me the t by itself, and I'll have 1,000 ln of 0.61 over ln of 0.5. So let's type that in. 1,000, whoops, I guess I should use parentheses here. 1,000 ln, try again. Ln of 0.61, close the parentheses for the numerator, and we're dividing that by ln of 0.5. And we get 713.12. This is a time. And remember that our units from earlier for the times and the half-lives were years. So it's going to take a little over 713 years for this radioactive element to decay to 6.1 grams. Okay, in this next example, we're going to talk about another common type of radioactive decay problem. It's one that involves the element carbon-14. And carbon-14 is something that scientists use to measure how old things are, because you can measure how much carbon-14 is present in that living object. And we know the half-life of carbon-14 is 5,730 years, so scientists can measure based on that how old the object is. So in this example, in 1998, the canvas of a painting attributed to the painter Vermeer, who was a painter from 1632 to 1675, was found to contain 99.5% of the carbon-14 that is present in living trees. We want to know how long ago was the canvas made, and we want to note that the half-life of carbon-14 is 5,730 years. So this is a process that authenticators would use to determine how authentic a particular painting is. If somebody is claiming it to be made from one of the masters, this would be a way to decide that. So what we're told is that we have this carbon-14 being measured in the canvas of the painting. And because that's a radioactive decay type of scenario, we're going to use our same old model that we've been using on the previous problems, which says that the amount present, P of t, is the initial amount, P sub 0, e to the RT. And what we're told here is that the half-life of carbon-14, which is a time, remember, is 5,730 years. Now right away, that half-life is going to be used to determine the R, or the rate of decay, that we're going to be using in this formula. So you can use your shortcut here, that formula that we talked about a few minutes ago. The radioactive decay rate, R, is always going to be the ln of 0.5, and that 0.5 comes from the fact that we're ending up with half of our initial amount left, divided by our half-life. So in this problem, our half-life for our element is 5,730 years, so that's what we are going to plug in for this R. So our model becomes P of t equals P sub 0 e to the ln of 0.5 divided by 5,730 times t. Now they don't tell us in this problem the initial amount of carbon-14 that was present in the painting whenever it was created. They do tell us that when it was found, it contains 99.5%. So in 1998, which is when this painting was found, there was 99.5% carbon-14 present. Now, even though we don't know how much of this carbon-14 was initially present, we do know that in 1998, we have 99.5% of it left. So we have 0.995 times, or of, this initial P sub 0 left at 1998 in that particular year. So what we can do is use this value right here as our amount left. So that's going to be our p-value, and we're going to solve this for t to find out what time it took for the carbon-14 to decay to 0.995%, or 99.5% of the original amount. So we're going to substitute in 0.995 of P sub 0, so 99.5% of the original amount, and we're going to find out what time it takes for this carbon-14 to decay by that much. So we're solving for t. Now this is similar to an earlier problem we did, where initially it looks like we have too many variables, but when I go and divide through by that coefficient P sub 0, it ends up canceling out on both sides. So even though we didn't know what that P sub 0 was, it wasn't necessary to know it. We just needed to know the percent of it that was left over after this time t. So I've canceled out my P sub 0s. Now this becomes an equation only in terms of t. So to solve for it, I'm going to do my ln's of both sides. And that ln and that e are going to cancel each other out. So I get ln of 0.995 equals ln of 0.5 over 5730 times t. T is being multiplied by this fraction, so to solve for t, we're going to want to multiply the left side by the reciprocal, or we're multiplying both sides by the reciprocal, but it cancels out on the right side. And on the left side, we get the reciprocal of 5730 divided by ln of 0.5, and that's being multiplied by this ln of 0.995. So if you wanted to group this together a little bit better, it's 5730 ln of 0.995 all over ln of 0.5. So let's go ahead and plug this into our calculator. And we get a t that's equal to 41.44. I'll round off to 2 decimal places. And what are the units on these t's? Well, the units on our half-life was years, so that's the same unit we want to be using for our t here as well. So what does this mean? It means that it took 41.44 years for this carbon-14 to decay to 99.5%. So it took just over 41 years for the carbon-14 to decay to 99.5% of the original amount. So that implies that this canvas is just over 41 years old. So is it possible then for our master painter Vermeer to have painted this if he lived back in the 1600s, but we found this painting in 1998? No, not possible. It just hasn't been enough time for that carbon-14 to decay. So this is not attributed to Vermeer. So this painting must be a fake, okay? Because it can't be authenticated to exist during his time period. All right, the next kind of example that we're going to look at uses a slightly more complicated formula, but it's still an exponential decay and sometimes a growth situation. So this is called Newton's law of cooling. There's also a Newton's law of heating. And in this case, for Newton's law of cooling, which is a decay situation, the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings. So let me give you an example of what we're going to be talking about. We're going to be taking something hot, like a cup of coffee, and taking it outside on a cold day. What's going to happen to the temperature of that coffee as it sits outside in the cold? Well, obviously the coffee is going to cool off and its temperature is going to drop, or it's going to decay. So that's what Newton's law of cooling is all about. And so what it says is its rate of cooling of the object is proportional to the temperature difference between the object and its surroundings. We're going to let T sub S represent the temperature of the surroundings. So this would be like the temperature of the cold air outside. Then the temperature of the object at any time t is going to be given by this formula, T sub T, so the temperature at any time t is equal to the surrounding temperature plus the initial temperature minus the surrounding temperature times e to the negative kt, where k is a positive constant and T sub 0 is the initial temperature of the object. So it's a slightly more complicated looking formula, but it's relatively simple to use if you know what everything means. So let's take a look at an example. A cup of coffee is taken from the microwave at 210 degrees Fahrenheit. and it's placed in a room that has a temperature of 68 degrees Fahrenheit. So a really hot cup of coffee is being put in a cooler room, a much cooler room. Find a formula for the temperature of the coffee at time t if the temperature after 5 minutes was 150 degrees. Okay, so let's see if we can identify some of these variables up here. Do we know the temperature of the surrounding air? Well, that's the temperature of the room, and that was 68 degrees. Do we know the initial temperature of the coffee? Yes, that's what it was when it came right out of the microwave, 210 degrees. So according to this model, our temperature at any time t is going to be the initial temperature, the temperature of the surrounding air plus the initial temperature minus the temperature of the surrounding air times e to the negative kt. And let's plug in what we know. We know that the temperature of the surrounding air was 68 and the initial temperature was 210, and I'm going to use that 68 again right here. So if we simplify this, we get 68 plus 210 minus 68 is 142. Now this would be our model, except we aren't told K directly. So we still need to figure out what K is, and then we'll have our model. So in order to figure out K, we need a time t and a temperature t that go together so that we can substitute those in and then solve for K. And that's what this second sentence is all about. We are told that the temperature after 5 minutes is 150 degrees. So I'm going to plug in 150 degrees on the left side, that's where your temperatures go, and I'm going to plug in 5 for this little t up here. And we just have to keep in the back of our mind the fact that I'm using minutes now for my units for time. So I want to use that consistently throughout the rest of the problem. Now on this example here, in order to solve this, we have to isolate this exponential part. It does have a coefficient, but before I can divide through by that coefficient 142, you must move this 68 over to the left side first. You want to undo that addition first. So 150 minus 68 is going to give me 82. And now I can divide through by my coefficient 142. So I get 82 over 142 equals e to the negative 5k. I can take my ln of both sides. The ln and the e cancel out, just giving me negative 5k. And I can finish solving for k by dividing both sides by negative 5. So k is ln of 82 over 142 divided by negative 5. So it's pretty messy. So here's what our final model is going to look like. The temperature at time t is temperature of the surrounding air, which is 68, plus this temperature difference, which is that 210 minus 68, which will be 142. And now I know K, so I'm going to substitute it in. And notice here that you need to do e to the negative k, but this k right here has a negative in it in the denominator. So negative cancels out, so this is going to be ln of 82 over 142 divided by a positive 5 times t. So the negative that was in front of the 5 cancels out the negative that's supposed to be in front of that k. So this is the model that we are going to use to answer some additional questions down below. So based on that model, you tell me any time and I can tell you what the temperature of the coffee should be, or you tell me what temperature of the coffee you want and I'll tell you how long you're going to have to wait until it cools off to that temperature. So let's try this next example. What is the temperature of the coffee after 15 minutes? So this time I'm given t, and it's in minutes, which is good because that's what I was using before. So all we have to do is plug in a 5 right here into our model. So the temperature, T, is going to be 68 plus 142 e to the ln of 82 divided by 142 all over 5 times 15. And now we're going to want to type this into our calculator very, very carefully. So we're going to type in 68 plus 142 e raised to the ln of 82 divided by 142, and then I'm dividing all of that by 5, and then I'm multiplying that by 15. And then I want to close my parentheses. And I get 95.34. And then the units on this, remember what we just found here was this big T, so this is our temperature, so this would be degrees Fahrenheit. So after 15 minutes, the coffee has cooled from 210 all the way down to 95.34 degrees. Okay, so in that example we were given the little t and we wanted the big temperature T. In the next example, it's the opposite of that. So this time we want to know, when has the coffee cooled to 100 degrees Fahrenheit? So how long are we going to have to wait before the coffee cools off to 100? So this time we're given the temperature T 100, and I'm going to put 100 over here on the left side. So 100 equals 68 plus 142 e to the ln of 82 over 142 divided by 5 times t, that unknown time t. So this is a bit messy, but still doable. We're trying to isolate this exponential part, so we're going to need to get rid of this coefficient, but before that even, we've got to get rid of that 68. It's positive, so I'm going to want to subtract it over to the left side. So 100 minus 68 is 32. And now we have this coefficient in front of the e to get rid of, so I'm going to divide both sides by 142. And that gets me the e isolated. And now I'm ready to take the ln of both sides. And that should cancel out my e, giving me just ln of 82 over 142 times t. And to finish it off, oops, I lost my 5 somewhere up here. Let me put it back in. It was divided by 5. I forgot that. So to solve for this t, I'm going to want to multiply by the reciprocal of this fraction. So t is going to be the reciprocal of this, so 5 over ln of 82 over 142 times what I originally had on the left side, so ln of 32 over 142. So it's pretty messy looking, but if you wanted to consolidate it a little bit more, it would be 5 ln of 32 over 142 all over ln of 82 over 142. And so we're going to type all that into our calculator. So we'll take parentheses 5 ln of 32 divided by 142, close the parentheses for the ln, close the parentheses for the numerator, and then we're going to divide that by the ln of 82 divided by 142, close the parentheses for the ln. And we get 13.57. And this was a little t, so this was a time, and the units we were using in this problem were minutes. So it's going to take 13.57 minutes for the coffee to cool to 100 degrees Fahrenheit. Okay? All right, the next example is a little bit different. This time you have a filtering system which water runs through. It's going to send water through a series of charcoal filters, and each time the water goes through one of these filters, a layer of pollutants gets removed. So when the water runs through this series of charcoal filters, each layer removes 30% of the pollutants present. So that is, the amount remaining of pollutants is 70% of the amount present prior to going through each filter. We want to find a model to represent this situation. So each time the water runs through a filter, it's removing 30% but leaving 70% of those pollutants still in the water system. So we want to try to figure out some kind of model for this. So let's start with our basic formula. P of t equals P sub 0 e to the RT, and see if we can figure out some way to represent this situation. Since we aren't told the initial amount of pollutants present, we don't know this P sub 0. But we do know that after one time through the filter, we're left with 70% of the pollutants left over. We lose 30%, but we're left with 70%. So if we started with P sub 0 initially, one time through the filter means we're going to have 0.7 of the initial amount of pollutants still left over. So we're using that idea of taking a percent of our initial amount, even though we don't know what the initial amount was. So my time here isn't really time, it's the number of times through the filter. So here my T is how many filters I'm going to need. So one filter leaves me with 0.7 of the original amount of pollutants. And that's when my T here, my number of filters, is 1. So that's sort of a T and a P that go together so that I can try and solve for this decay rate R. So I'm going to divide through by P sub 0 on both sides. They cancel out, and I'm left with 0.7 equals e to the R, because R times 1 just is R. If I take the ln of both sides, the ln and the e cancel out, so we just get that R is ln of 0.7. So now we have enough information to write out sort of a model. It's not perfect because we don't know this P sub 0, but we do know what R is. So this will be e to the ln of 0.7 times t, where t is the number of filters and p is the amount of pollutants left over in the water. Okay, so here's our model. So if you were the mayor of a city and you were trying to clean up your water supply, this would be a situation that you would have to consider. And you'd also have to budget it in, because each filter can cost up to $4 million. And in this example, each filter costs $4 million. So what would it cost for the city to remove 95% of all the pollutants in the water? If you want your water to be 95% clean, how many of these filters are you going to need? And each one costs $4 million. So let's see how we can measure that. Well, if we want our water to be 95% free of pollutants, then how many pollutants would be left in the water still? If it's 95% gone, that means we'd have 5% left. In other words, we would have 0.05 of the original amount present still in the water. So that's the P that we're going to use on this side over here. So if we want our water 95% clean, then we would expect to have 0.05 times the initial amount of the pollutants left in our water. And this model says that that amount has to equal P sub 0 e to the ln of 0.7 times t. So if I divide through by p sub 0, these are going to cancel out. I get 0.05 equals e to the ln of 0.7 times t. Take an ln of both sides. That cancels out the e, giving me ln of 0.7 times t. And to finish solving for t, I can divide by 0.7. So my t is going to be ln of 0.05 divided by ln of 0.7. And this t, remember, is the number of filters needed. So I'm going to round here a little bit. This is going to give me 8.399. So if we round that off to maybe 9 full filters to guarantee that we're at least 95% clean. If we only used 8 filters, then we wouldn't quite be at that 95% mark. So we're going to need at least 9 filters to be at 95%. So this was actually 8.399, but I'm rounding it up to 9 full filters. Each one is $4 million. So if I multiply 9 times 4 million, that's going to cost the city $36 million to have 95% clean water. Okay? So what would it cost then to have the water be 99% clean? Well, if you want your water to be 99% clean, then that would mean there's 1% of pollutants left, or 0.01 times p sub 0 left in the water. So this time we're going to let our p on the left side be 0.01 p sub 0. Set it equal to p sub 0 e to the ln of 0.7 times t. Divide by our coefficient p sub 0 so they cancel out. And then we're going to take an ln of both sides. The ln and the e cancel out. So our t is going to be, when I divide both sides by ln of 0.7, this time our t is going to be ln of 0.01 divided by ln of 0.7. So you can start to see the trend here. Before we had t was ln of 0.05 divided by 0.7 for 95% clean, and now it's ln of 0.01 divided by ln of 0.7. So let's see how much this is going to be. 0.01 divided by ln of 0.7. And again, I'm going to round up. So this is approximately 13 filters needed. So if I multiply 13 times 4, then that makes this $52 million in cost for the city. Okay? So saving ourselves just a little bit of work here. If we want the water to be 99.9% clean, then what percent would be left? Well, 0.1% would be left, which as a decimal is 0.001 of the initial amount. So if you kind of remember our trend here, instead of having to solve this all out again, the time or the number of filters that it's going to take is going to be ln of the percent as a decimal that would be left over. That's how we got these numbers on top. So 95%, we needed 0.05. For 99%, we needed 0.01. So for 99.9%, we would need 0.001. And both of these were being divided by that ln of 0.7. So let's figure out what this would be. Whoops, one too many zeros. So I'm going to round that up to the next highest amount to ensure that we're getting at least 99.9%. So this is going to be about 20 filters needed. Each one is $4 million, so that means the total cost to the city would be $80 million. So even though we just went from 99% up to 99.9%, so only a percentage change of 0.9%, you can see that the cost went up by close to $30 million. Okay? All right, the last example and application that we're going to talk about is something that you've probably heard about, things like the Richter scale that is used to measure the intensity of an earthquake. A lot of times when a physical quantity can vary over a very large range, so from very small numbers up to very large numbers, it's more convenient to take the logarithm of those values so that that range is narrowed down, so we're not talking about such a huge range of values. And it gives us a much more manageable set of numbers to deal with. The Richter scale is an example of this. It measures the intensity of earthquakes. Also, the pH scale uses logarithms and it measures acidity. The decibel scale measures loudness of sound, and light intensity also use logarithms to help make this manageable set of numbers easier to work with. So the Richter scale that we use to measure the intensity of an earthquake is given by this model. So this is just a formula that you would need to know, and it says that M is equal to log of I over S, where I is the intensity of the earthquake and S is the intensity of a standard earthquake. So what we're going to take a look at is the comparison of two separate earthquakes. The Northbridge, California earthquake had a magnitude of 8.6 on the Richter scale. That would be this M value right here. So that's your Richter scale number. The earthquake in Japan in 1995 had a Richter scale reading of 7.2. How many times more intense was the California earthquake? So notice the two Richter scale values, 8.6 and 7.2, they're not really that far apart. But because we are really looking at logarithms and using logarithms to help us measure these intensities, there is going to be a much bigger difference in their intensities when we do a comparison. So let's write down what we know so far. We know that in California, the Richter scale number, this M, was 8.6, and in Japan, the Richter scale, this M number, was 7.2. Now, we don't know the actual intensity of each one. We just know what its Richter scale number is. So I am going to let I be the intensity of Japan's earthquake. And I'm going to let the intensity of California's earthquake be some constant times the intensity of Japan. So look at how I'm defining this. I'm trying to be a little bit strategic here. I don't know the intensity of either one, so you could call these two different values. But we know that the California one had a higher Richter scale, so it was more powerful than the Japanese earthquake. So if I know that the Japanese earthquake has an intensity that I'm going to call I, then the California one would be K times more intense. So I'm going to, instead of creating two totally different variables, I'm letting the intensity for California be just some constant K times the intensity of Japan's. So let's see how this helps us out. I'm going to start with Japan. Using this formula for the Richter scale, the M number is this 7.2, and this is supposed to equal log of I over S. For California, this would be 8.6 equals log of its intensity, and its intensity is K times I over this standard earthquake. So this S value is kind of like a given, a constant amount, even though we're not told exactly what it is. It turns out we don't really need to know what it is to figure out the problem. Now the key to these earthquake problems is really those properties of logs. We're going to use those to help manipulate our two different formulas here and try to compare them. So if we take a look at this California one, 8.6 equals the log of this quotient. And what you want to remember about properties of logs is the log of a quotient becomes the difference in the two logs. So we take the log of the top minus the log of the bottom. And then if you look at what we have inside here, this is really k times I, and that's a product. So the log of a product becomes the sum of the two logs. So I'm going to break up log of k times I into log of just k plus log of I minus log of s. So all I did was I broke up this entire log formula into all of its individual parts. Now you may be thinking, okay, this doesn't look like it's really getting me anywhere, but take a look at what we know about Japan and let's do the same situation over here. Let's do the same steps. We have the log of a quotient, so this could become the log of the top I minus the log of the bottom s. And what's the clever part of these kinds of problems is noticing that log of I minus s is 7.2. So this log of I minus s must be 7.2 as well, because we referenced the intensity of the California quake in terms of the intensity of the Japanese quake. So that was the key, using this k times I and comparing it to the original intensity I. So by doing that, I can now substitute in this whole expression becomes a 7.2, and now what we're left with is just an equation with only one variable, k. So to solve for it, I'm going to subtract 7.2 over to the other side. 8.6 minus 7.2 is 1.4, and let's see if we can figure out what this k is. Now to solve for k, you want to undo the log, and what's going to undo a log is an exponential. Now what's the base on this log? This is just an log, so if you see an log with no base, you have to remember that means a common log, which means a base 10. So we can rewrite this as 10 raised to the 1.4 equals to k. And if we go to our calculator and do 10 raised to the 1.4, we get about 25, and I'm just going to round that off. So this is about 25. Now what did this k represent? It was how much more intense the California quake was compared to the Japanese quake. So California's quake was 25 times more intense than the Japanese quake. And you wouldn't essentially think that based on how close the Richter scale values were, 8.6 to 7.2, that's only a difference of 1.4. But you have to remember that that's a difference of 1.4 in a logarithm scale. So that really represents that California quake being 25 times more powerful than the Japanese quake. So you probably will see some of these Richter scale types of problems in your homework and in your book. So just remember this sort of trick of letting the more powerful one be k times more intense than the less powerful one. Use your properties of logs to break it up, and then you can substitute in the Richter scale value for the smaller quake into this equation and solve for the intensity factor. Alright, that concludes our lecture on applications of logs and exponents. Good luck!